Welcome to The Explainer. Today, we are pulling back the curtain on the technology that powers pretty much all the AI tools we use every single day. We're going to break down this massive step-by-step industrial process that takes just raw data and turns it into a large language model.
So, how do models like ChatGPT actually get built? How does it go from being a blank slate to this helpful assistant we can talk to? Well, it's definitely not a single magic step. It is a massive, multi-stage industrial process. We're talking huge amounts of data and just incredible computing power. Okay, let's dive into it.
All right, to really understand this whole thing, we've got to start with the absolute core principle of what a large language model, or an LLM, even is. And at its heart, it's actually built on a surprisingly simple idea. Okay, so at its core, it's all about probability. A language model's entire job is just to predict what comes next. Think of it like a super-powered autocomplete. By analyzing billions upon billions of sentences, it learns all the patterns. And I don't just mean grammar and facts. It learns styles of reasoning, all to figure out which word is most likely to follow the last one.
So, for example, let's take this simple sentence fragment here. The model's entire training, all that work, is focused on just one task: using this context to predict the single most probable word that comes next.
And of course, based on everything it's learned, it would predict cheese with a super high probability. This task has a name. It's called autoregressive modeling. And by just repeating this process over and over and over again, one word at a time, the model can generate entire paragraphs. So this is the really crucial point. This simple, repetitive prediction, that's the foundation for literally everything that follows.
Okay, so that brings us to what you could call Act 1 of building an LLM, the massive pre-training phase. This is where the model basically goes to school, so to speak. It's where it builds its raw foundational knowledge about the world.
The goal here is pretty straightforward. Create the most comprehensive base of knowledge you possibly can. And how do you do that? Well, you feed the model an absolutely stunning amount of text, from books, articles, code, and a huge portion of the public internet. But, as we all know, the internet can be a very messy place.
Right, so you can't just dump the raw internet into the model. It's not that simple. First, it has to go through this really rigorous industrial-scale cleaning process. I'm talking billions of pages get downloaded, the actual text is pulled out from all the messy code, harmful and low-quality stuff gets filtered out, and all those repeated paragraphs and headers get deleted. Then, at the very end, all that data is mixed together, but they give more weight to high-quality sources like academic papers to create the final training dataset.
Now, this brings us to one of the most important, honestly, game-changing discoveries in modern AI. How the industry figured out how to improve these models with almost mathematical certainty. And the secret? Well, it turns out it was just scale.
You see, researchers found something really surprising. Unlike a lot of other machine learning, with LLMs, the performance just keeps getting better and better the more data and computing power you throw at them. If you actually plot the model's performance against the amount of compute on this special chart, a log chart, it forms a nearly perfect straight line. And this is huge because it allows companies to predict exactly how good a bigger model will be before they spend a single dollar to build it.
And the scale we're talking about here, it is just staggering. A token is basically a piece of a word, and a state-of-the-art model, something like Meta's Llama 3, was trained on over 15 times trillion of them. It's almost impossible to wrap your head around that number.
And as you can probably imagine, that kind of scale requires an absolutely enormous investment. We're talking about training a single large model, which can involve over 16,000 of the world's most advanced GPUs running 24/7 for months on end. That pushes the estimated cost for just one single training run into the tens of millions of dollars.
All right, let's move on to Act 2. After all that pre-training, what we have is an incredibly knowledgeable model. You can think of it like a digital scholar that has read an entire library. But, and this is a big but, it's not a useful assistant yet. It knows a ton, but it doesn't actually know how to follow your instructions.
And this right here illustrates the problem perfectly. On the left, you give a pre-trained model a prompt, and what does it do? It just continues the pattern. It sees something that looks like a question, so it spits out another question. But look at the right, the post-trained assistant. It understands your intent. It gets what you want, and it follows the instruction, giving you a really helpful answer.
So, how do they make that transformation happen? Well, it's done in a two-step post-training phase. And this whole phase is designed specifically to align the model with what we actually need to make it genuinely helpful. The first step is called supervised fine-tuning, or SFT. And the key thing to get here is that this step doesn't teach the model new facts. All that knowledge is already in there from pre-training.
Instead, it's shown thousands and thousands of high-quality examples of questions and answers written by real people. This is what teaches it the format and the style, how to behave like a helpful assistant.
Okay, so the second step refines that behavior even more. The model generates several possible answers to the same prompt, and then a human, or sometimes another AI, picks the best one. By doing this over and over, you're teaching the model what kinds of answers people actually prefer. You're pushing it to be more helpful, more honest, and really importantly, safer.
So this brings up a really important question. If we're teaching the model to be preferred by humans, how do you measure that? It turns out the old metrics they used during that pre-training phase, they just don't apply anymore.
Back in the pre-training days, a metric called perplexity was the standard. The easiest way to think about it is as a measure of the model's confusion or hesitation. So a low perplexity score is good. It means the model is really confident about what word it's going to predict next.
But for an AI assistant, right, we don't just care about how confident it is, we care about how helpful it is. So now the gold standard is direct human feedback. You have platforms like Chatbot Arena, where users interact with two totally anonymous models, side by side, and they just vote for which one gave the better response. This creates a leaderboard based purely on what humans actually prefer.
So this entire process we've walked through, from that initial pre-training all the way to the preference tuning, it all relies on one thing: a vast ocean of human-generated data. But as those scaling laws keep pushing models to get bigger and better, their appetite for data is just growing exponentially. And this leaves us with a fascinating and frankly, an absolutely critical question for the entire future of AI. What happens when we run out of internet to train on?